Hello everyone, welcome back to another discussion in dynamics. Today we will continue kinematics of rigid bodies. And this topic actually has 4 subtopics. So last week we covered rotation about fixed axis, velocity analysis, and today we will focus on instantaneous center of rotation. And on Friday we will talk about acceleration analysis. But today we will talk about ICR. So plan for today is brief lecture review and then 2 examples. So without further ado, let's dive straight to our discussion. Okay, so I just would like to define what is instantaneous center of rotation. Actually, maybe let me start let me start once again. So in the last video, yes, on Friday, we talk about velocity analysis, yes, which is, in my opinion, very straightforward approach to figure out what is the velocity in the system. Yeah, you just write this equation between 2 points multiple times, yes, until the problem is done. Yeah. Today we will talk about equivalent approach, which I call geometric approach. Yeah, and this is called with some mysterious term called instantaneous center of rotation. Why is it called geometric term? So let me tell you. Let us consider a rigid body, okay? And let's say that we know everything about 2 points on that rigid body, okay? We know what is the velocity at point A, and we also know what is the velocity at point B, of course, vector-wise. To find instantaneous center of rotation, we have to follow following steps. First of all, we must find perpendicular direction to this velocity vector, and of course perpendicular direction to this velocity vector. And at the cross section we have our ICR. This is instantaneous center of rotation. That's it. Clearly geometric approach, yes? And now, if you guys know, for example, this distance, if you know this distance, let's call it D, then you can write that VA, I mean magnitude-wise, of course, is equal to omega body times D. Okay, and that's how we find omega body. Omega body is equal to VA divided by D. Okay, or if you know this distance, let's say L, okay, then VB is equal to omega body times L. Questions? Are there any questions? Okay, so we will use it 700 times today. Okay? So what do you think? Example number 1? Yeah, I see that some of you are writing still. Yeah. Let's do example number 1, okay? So I would like to, topic of today is instantaneous center of rotation. However, I would like to solve this problem using velocity analysis, okay? And then we'll solve it again using instantaneous center of rotation. This is my plan for today, okay? So just, you know what to do. Read and understand the problem statement. Or if you're watching this video, just feel free to pause the video and read it. Okay, so what do we have in here? We have 3 bodies, right? We have bar AB here. We have bar BC here, and we have our color C. Yes, that color is constrained. It can only move along this direction. I hope you can all see that. So we know geometry, and they only told us that we know omega of this body. Yes, we don't know velocity of any other body or any other point. Yes, and they ask us to find omega of this body. So let's already assume, pre-assume that this is rotating in a positive direction. Okay, so it will be rotating this way, omega AB, and VC. We have to find velocity of this point, of point C. Okay, so let's do our velocity analysis approach. So what I would do, I would first of all write velocity analysis between points A and B, or B and A, let's say B and A, B and A. Okay, so I will write VB is equal to VA plus omega of certain body times RBA. And I'm not going to ask you what omega of which body is that. It must be omega AB. Yes, it must be omega of this body. Why? Because A and B belongs to bar AB. Okay, so first of all, VA is 0, clearly. This guy is 0. 0 vector, because A is fixed. Exactly, this is what we see in the picture. So now, VB will be equal to 0, 0, omega AB, we assumed positive direction, times this vector. Okay, let's draw it in the picture. RBA. So this will be this red vector, right? It will be this vector. RB with respect to A. And I hope that you guys all see that at this instant, this vector is 0 minus L, 0. 0 minus L, 0. Okay, let's do our determinant. IJK, 0, 0, omega AB, 0 minus L, 0. So this will be L omega AB, 0, 0. Great, but we don't know omega AB, right? We must leave it like that for now. Any questions to what happened on the board? Okay, so just to solve the problem, what we're gonna do next? Anybody wanna give it a shot? Velocity analysis between two other points. Yes, nobody said that, but I know that you all thought that. Yes, so we're just gonna do velocity analysis between points C and B. Okay, so let's write it down. Velocity analysis between points C and B. So I'm just gonna write our expression. VC is equal to VB plus omega of certain body times RCB. And that certain body is, of course, the other road. Yes, it will be road BC. Okay. So in here we can just write that VC is equal to L omega AB, because this is what we just found, plus 0, 0. What was the value of omega BC? Let me scroll up the board. It was 20, and this is rotating in a positive fashion, yes? Okay, so it's 20 times this vector. I just drawn it in the picture. Let me scroll up the board. RCB is here, and its components are L, 0, 0. L, 0, 0. Okay, let's do this determinant very quickly. ijk 0, 0, 20, L 0, 0. This is 0. This is 20L, and this is 0. Great. So our VC will be equal to L omega AB 20L 0. Okay, questions? Any questions so far? Yeah. This is, so you guys can see that in era of computers, this can be all done by computer, yes? Because you can see a clear sequence in what we do, yeah? Humans don't no longer do that, yeah? We just do it for you just to see what we want to show you what computers are doing here, yes? Yeah. This is all automatic. This can be all done automatically. Why? Because we repeated exactly the same things twice, yeah? Okay, but let's continue. And there are no questions, yes, so far? Okay, however, I think we can say something more about this vector, VC. We can say something more, yeah? Because if I scroll up the board, you guys can see that our VC must be aligned with this constraint. Yes, this is our trajectory of point C. Do you see that? Yeah. So do you agree with me if I write that VC vector will be equal to magnitude of VC times, I believe, cosine theta sine theta 0. What do you think about that? Is this true? Yeah, our VC will be either aligned here, yeah, or it will be pointing this way maybe, yeah. So I should probably put like plus minus here. I don't know, plus minus, yeah, something like that. But anyway, my point is that the direction of VC will be this direction, yeah. Okay, so let's just plug this value in here. So we have VC cosine theta, VC sine theta 0. Okay, and we ended up with two equations, yes? This equation and this equation. So we can write VC cosine theta is equal to L omega AB, and also we can write VC sine theta that is equal to 20L. Okay, we have two equations and two unknowns, by the way, because this is an unknown, this is not known, VC, and omega AB is not known. Solvable, yeah. Okay, so let's solve it. So I think that from this expression, we can see that VC is equal to 20L divided by sine theta. So just plug in values. This will be 20 times 2.5 divided by sine 45. If you grab calculators, you will obtain that this is equal to 50 square root of 2 feet per second. Yes, feet per second. Okay. And once we know VC, we also know omega AB, because from this expression right now, from the first equation, we have that omega AB is equal to VC cosine theta divided by L. So this will be 50 square root of 2 times cosine 45 degrees divided by 2.5. So this will be exactly 20 radians per second. Okay, so now vector-wise. Omega AB is equal to 0, 0, 20. Radians per second. So this will be counterclockwise. And our VC, we also obtain the positive value, yeah? So that will be 50 square root of 2 times cosine 45 degrees, sine 45 degrees, 0. So if you grab your calculators, you will obtain that our VC is actually 50, 50, 0 feet per second. That's the end of the problem. How do you like it? How does it look like from your perspective? Doable? Yeah. Velocity approach? Follow the recipe. Yes. Yeah. Just quite easy in my opinion. Yeah. Unless there are questions. Okay. So now let's do exactly the same problem, but using our new approach, instantaneous center of rotation. Is it okay with you? Let's do it. Okay. So please familiarize yourself. I'm kidding. Yeah. Just we're gonna do exactly the same problem. Yeah. Actually, let's do maybe only half of it. Okay. So guys, let's find instantaneous center of rotation. Our goal is to find instantaneous center of rotation for this bar. Okay. Let's find ICR for bar BC. Okay, so do you remember that recipe from the beginning of the discussion? We must find two velocities of 2 points on that bar. So I think that, do you want to go for it? Yeah. Do you want to detect these 2 points? Velocity we already know. Yeah. Scott, do you want to do it? Yeah. I thought you were nodding your head. Like you were like, okay. So anyway, I want to find, so what is the velocity of point C? Anybody can tell me maybe? It has to be aligned with this constraint, right? Yeah. So let's say that this will be our velocity. I don't know. Maybe this one, maybe the other one. I don't care. And now you guys can tell me what will be the vector of VB. It will be horizontal, it will be vertical, it will be inclined. It will be horizontal, yes. And why? Because of this constraint. Yeah. Trajectory of point B is this circle. Yeah. This is trajectory of point B, yes, because this is our pendulum. Right? Yeah. So at this point, our VB will be, I don't know, facing either this way or the other way. Right? Okay. So we found directions of 2 velocities, yes? So now the next step is to draw perpendicular line to these 2 directions, yes? So first perpendicular will be here. This is 90 degrees, right? And second one will be here. This is 90 degrees. And our ICR is at their intersection. So you can clearly see, guys, that point A is equal to ICR of bar BC, yes? Do you see that? Cool. Okay, so let's find ICR of bar BC. Point A is ICR of bar BC. Okay, and by the way, we know omega BC, yes? Omega BC is 20 radians per second. They told us, Yes, in a problem statement here. Okay, so let's find the velocity of point C. Vc will be omega bc times this distance. Let's go to d. Yeah. Can you guys tell me how much is d based on the picture? Yeah, it's square root of 2 times L. Perfect. So this will be square root of 2 times L. Let's plug in values. So that will be 20 times square root of 2 times 2.5. This is 50 square root of 2 feet per second. Exactly what we obtained 5 minutes ago. Yes? Okay, but we found magnitude. We found magnitude. So now let's do vector-wise. So our VC will be equal to VC times, you guys told me, cosine theta, sine theta 0. Let's plug in values. So that will be 50 square root of 2 times square root of 2 divided by 2, square root of 2 divided by 2, 0. This is exactly 50, 50, 0. Okay, exactly what we obtained using our velocity approach. So yeah, so my goal today was just to show you that they are equivalent. Yes? And the rest of the problem, you know how to solve. The rest of the problem you will solve by your own. You can use it, you can use either instantaneous center of rotation again, or maybe you can just look at your notes we just put together 5 minutes ago. Questions? So I prefer velocity analysis actually, because I prefer to program my computer to do all of my calculations for me, okay? So instantaneous center of rotation is kind of geometric approach, so it's good for pen and paper, yeah? Yeah, that was actually faster than what we did earlier, yeah? We solved that problem much faster than the other one, yes? However, in nowadays era of computers, I program my computer to do all the tedious job for me. And I wanna enjoy my life while my computer is working for me, okay? However, so I usually go for velocity analysis. Yeah, they are equivalent, so you can listen to you can follow my advice, or you can do whatever you want. Yeah. However, I think that in next topic, sometimes it's good to know how to find. In the future, maybe we will use instantaneous center of rotation once or twice, because it will speed up calculations tremendously. Yes, in the next topics. Okay, so just keep in mind that you know how to find ICR. Okay, we have question of Will. Yeah.
Is there a good way to know when to use ICR versus like is there any key things you should look for?
Yes, they come with experience.
Okay.
Yes. If you solve your homework problems without using solution manuals, you will probably gain experience. Okay, that's. Any other question? Yeah. I can answer this. I can give that answer to anything you ask me. Yes, in life. Yeah. How do you know how to tie your shoes? Yeah. At the beginning, you didn't know how to tie your shoes. Yes. It comes with experience. Yes. Yeah. How do you know how to walk? I don't know. It comes with experience. Yes. Okay. Example number 2. Please familiarize yourself with the problem statement before we start our solution. Okay. Anyway, do we have to familiarize ourselves with that problem statement? That was problem from Friday. Yes? Now, in Friday, we used velocity analysis to solve that problem, right? Today, we will use instantaneous center of rotation. So, okay. So, how about, actually, you know what? So let me maybe say something about that system. Okay, so we have three bodies again. Yeah, we have beam AB here. We have beam BC, and we have color D. Yeah, and color D is constrained. Yes, it can only go back and forth in the horizontal direction. Yes. Okay, we know omega of this body. We know omega AB. It is equal to 2000 RPMs. We know geometry, and they ask us to find velocity of that point, velocity of point D. Okay, so I would like to start that solution with let's find ICR for beam BD. Okay, let's find ICR for BD. Yeah, I think Professor Sony even calls it IC. Yeah, he does not call it ICR. IC. Okay, let's do that notation. Let's find IC for beam BD. Okay, I don't know. Do you want to do it, guys? So let's follow the recipe I gave you at the beginning. Let's find 2 points that we for sure know how their velocity vectors look like, yeah? For beam BD. So first point is naturally D, yeah? Velocity D will be pointing, let's say, this way, for sure. Or maybe the other, or maybe it will be flipped, yeah? So I think that you don't mind if I just draw this line here. Yeah, so ICR will be somewhere, IC will be somewhere on that line. And this is, of course, it's of course 90 degrees. Okay, anybody else wanna go for the other point and the other velocity vector? John? Exactly, so you said that VB will be perpendicular to AB, exactly. And this is 90 degrees. Okay, so I must just extend AB, yes? So this is our IC. Great. So now what? So I think that now I would like to find omega of BD. Okay, this is our task right now. So omega of that bar. So we can either write something like that. We can either write VB is equal to omega BD times this distance, yes? Times this distance. So that would be RB with respect to IC. Okay? So that would be times RBIC, yeah? Just magnitude of that vector. Or we can just write VD is equal to omega of the same body times this distance. Let's say green vector. So that would be RD with respect to IC. So that would be RD with respect to IC. But of course, magnitude-wise. Yeah. Okay, so I think that I would like to find omega BD using this approach. But maybe before that, let's maybe figure out all the geometry, all the distances here, okay? So what is, for example, this distance, guys? Maybe you can tell me. I'm just gonna put this one here. So what is, for example, this distance? And this distance? So let's thought that this will be like x1, this will be x2. Okay, so I think that x1 will be, based on this triangle, it will be L1 cosine 40 degrees, or cosine theta. I believe so, yeah. So if you grab your calculators, you will obtain that this distance will be approximately 2.298 inches. Okay, now let's focus on x2. I believe that on Friday, we found this angle. I don't know how that letter is called actually in Greek. Is it psi? Okay, let's call it psi for the purpose of this discussion. Okay, I don't know. It is psi. I name you psi. Okay. So I think that x2 will be L2 cosine psi, right? And I think that on Friday we found that psi is approximately 13.9482 degrees. This is what we found on the video that I posted on Friday. So if you grab your calculators right now, you can obtain that x2 is approximately 7.764 inches. Okay, so our entire bottom of this big triangle, will be x1 plus x2, and this is equal to approximately 10.062 inches. Oh, you can see now how I call it geometrical approaches. This is clearly a geometrical approach. Okay, and I think that we know everything to find, for example, RDIC. So I think that if you look at that big triangle right now, big black triangle, this one, yeah, you guys can clearly see that our tan of theta is equal to RDIC divided by 10.062. Do you see that? Okay, so our RDIC is equal to 10.062 times tangent 40 degrees. Okay, grab your calculators and obtain that RDIC is equal to approximately 8.443 inches. Great. So we are done with our green friend. Yeah, this guy is done. Now let's focus on our red friend, this guy. Okay. So I think I want to do it here, if you don't mind. Can I do it here? So I think that cosine theta in that black triangle is equal to 10.062 divided by L1 plus RBIC. Do you agree? Okay, so now RBIC is equal to 10.062 divided by cosine theta minus L1. Plug in values and obtain that our RBIC is equal to approximately 10.135 inches. I think it all makes sense geometrically. So yeah, so hypotenuse is larger than, hypotenuse is larger than sides, yes? Yeah. This guy is 10.1 and more, a little bit more even, and this guy was 10.0. So yeah, hypotenuse is larger than the rest. Okay, did I lost anybody? Yeah. Clearly a geometric approach, right? Okay, so now I think that we know almost everything to solve that problem. So let's look at our equations. So I think, guys, do you mind if I just, instead of writing that magnitude, I will just write a scalar, okay? So it will be omega BD times R BID. And the omega BD is times RDIC. Okay, so I think that we know this value, we know this value, but we still don't know this value, and we still don't know this value, right? We don't know still don't know these two values. So let's find maybe VB. Okay, John, do you want to repeat what you said earlier? How to find VB? This vector. Yeah. No worries. I can tell you what. Yeah. I didn't want to like surprise you with that question. Yeah. Unless somebody else. Do you guys can tell me how to find magnitude of that vector in the fastest way? VB. Yeah. You are always active. Let's see if somebody else. Yeah. But yeah. Anna. Yeah. Exactly. Yeah. Yeah, but we can do it even faster, because this is like, do you remember our pre-recorded video on Wednesday? It was about fixed axis rotation. So look, A is fixed. Point A is fixed, yeah, so we can just write that VB, is equal to omega AB times this distance. And this distance is L1. Yeah, thank you. Thank you so much. Yeah. So that would be that crazy number, 209.4395. 209.4395 times, I believe, 3 inches. Yeah. So if you grab your calculators, you will obtain that this is equal to exactly 628.13. Oh no, sorry. 3185 inches per second. So this is our VB. Okay, now let's plug VB here, and let's obtain our omega BD. So now our omega BD is equal to VB divided by RB with respect to IC. So this will be 628.3185 divided by 10.135. If you grab your calculators, you will obtain that this is approximately 61.995 radians per second. Great. So we know omega of this body. And that body will definitely move this way, will rotate this way. So that will be omega BD. Yes. And by the way, on Friday, we found that omega BD, so on Friday, we found that omega BD was approximately 61.9929 radians per second. Yeah, if you don't believe me, look at your notes from Friday. Yes? What's the source of this discrepancy? Anybody? Or cause? What's the cause of this discrepancy? Anybody? John? Yes. Rounding error. Rounding error. Okay. Yeah, because we use two different approaches, yeah, and we don't keep like 700 digits after the comma, yeah. So there will be like some discrepancy in here, yeah. Okay, but I think that they asked us in the problem statement to find this vector, VD. Yes, so in order to find it, we must go for our other expression, this one. So our VD, finally, our VD will be omega BD, we just found, times R DIC. Okay, so that will be 61995 times, what was that distance? It was 8 something, I believe. 8.443. 8.443. Grab your calculators and obtain that VD is equal approximately to 523.424 inches per second. This is our answer. And on Friday we got that VD was approximately 523.4197 inches per second. The source of the discrepancy is exactly the same what John said earlier. It's a rounding error. Questions? So what happened today? We learned equivalent approach to velocity analysis, okay? So now you can run velocity analysis using actual velocity analysis or instantaneous center of rotation. Choose whichever you prefer more, okay? Thank you for today and hope to see you on Friday. Bye.